Hello everybody, welcome back to the channel, and in today's topic I'm going to be explaining the topic differentiation that you're required to know for your IGCSE extended mathematics. Now I do want to note that what I'm going to be explaining technically strays away from the GCSE topics a tiny bit, but what I'm going to try to do is that I'm going to try to explain the topic as intuitively as humanly possible. Now, to begin with, let's give an example, a standard example to motivate the topic. So, for example, if I have a car that's going to be traveling in a road, let's say a road like this, let's say I model the total displacement taken by the car, the total amount of distance taken by the car, with respect to time. So for example, our car is going to be, let's say, I'm going to call this axis time, and I'm going to call this axis x for displacement. So for example, let's say our car goes on like this and then stops like here. Now, as you can see, this graph tells us the information about car's movement. First of all, it shows us what position the car is in at a given moment in time, but it also shows another thing. It shows the rate of change. It shows how the rate of change of the car evolves as time passes. As you can see, the car's movement. As you can see, we see that the car's speed is increasing here, and we see that it's increasing faster here, and we see that it's increasing slower here, and then we see that it's pretty much near zero here. So we see that the graph tells us information about the speed of the car, and this concept of the speed is going to come up in a lot of other areas. Alright, so to do this, let us give an example. Again, let's say we have a random function like this, and this time it's just going to be an algebraic function with respect to x, and in the y-axis I'm just going to say it's going to be the function y equals f of x, and let's say it has a random graph like this. I don't know. Now you can see that again at these points the graph is increasing a lot, and at these points it's increasing less. It's increasing, but it's increasing slowly, and at these points it's decreasing. So we call this concept of the speed of a function, the quote-unquote speed of a function, the rate of change of the function. And you might see this rate of change in the same concept in other ways as well, and you might see it as a slope or a gradient, and pretty much all of these mean the exact same thing. And the reason this is called the slope, the rate of change, is that, well, the steeper the graph is, the faster it's increasing, right? So we say that the slope pretty much is the rate of change. Now, a thing you have to realize is that the rate of change of a function itself is also a function. And for example, at this point right here, the function is increasing in some rate, and at this point the function is decreasing in some other rate. And this is where the concept of the derivative comes into play. So we say that if for a function f of x, we call its derivative another function, we call it another function denoted by f prime of x. Now there are other methods of denoting the derivative of a function. We will cover them later. But essentially what this function is it's the rate of change of f of x at the point x. Alright, now let's continue. And this right here brings us to the concept of an instantaneous rate of change, which is a paradoxical topic in itself. Now, to explain this, I'm gonna again go back to our car example. So let's have a car. An axis is time. Hold on. Let's say the axis is time, and again this axis is a total displacement. Now let's say the car again moves like this. And when I say that I want to calculate the rate of change of this car at, let's say, some point A, now what does that even mean, right? Like, you can't really calculate the speed of the car at one moment. That's essentially what, like, essentially, if I gave you a snapshot of a car movements, and asked you to calculate its rate of change, its speed, you cannot do it, right? You need another time frame to give an approximation for that speed. And this right here is a paradox, and we get over it by not calculating the slope through 1 point, but instead calculating it through 2 points. So instead of calculating the rate of change at point A, we choose 2 points near point A, for example, point B and C, I'm going to say, and we calculate the total, I'm just going to write like this, we calculate the total change in Y between those 2 points, that I'm going to denote by delta Y, and we divide it by the total change in X between those 2 points. Or actually, our axis here is X and time, so I'm going to write delta X and delta time. And what this does is essentially it approximates the value, the rate of change of A near A. Now, going back to our algebraic case, so let's just again draw a random function, this time with respect to X, and we're going to call Y, and this is doing the graph of Y equals f of X. So let's just say it's some random graph like this. I just draw a random graph. Now, if we want to calculate, say, the rate of change at some point A, again, we choose 2 points near that A, and we calculate the slope, the average change in that region. So let's call this B and C. And what we're going to calculate, we're going to find out this change in Y, and we're going to divide that by this change in X. So the derivative in this, the estimation for our rate of change at point A would be delta Y over delta X. And what this value is that it's actually, I'm going to choose red. It actually is the slope of this line going through these 2 points. So what we're essentially doing is we're finding a chord near A, near the point A, and we're finding the slope of that. And this estimates the rate of change at A. Now here's the problem. This only estimates the rate of change, right? How do you find the exact rate of change at A? Well, simple. We just see what this value right here, the delta Y or delta X, approaches as these 2 points get closer and closer to A. The closer they are, the closer they are to the exact rate of change at A. And geometrically, that has a nice interpretation. As these 2 points get closer to A, we see that these 2 points get closer to A as well, and the chord connecting them essentially gets closer to the tangent line at A, to the tangent line of the at A, so tangent to the curve at the point A. And this is why we say that the slope, actually I'm going to write the last green color, the slope of the line tangent to a curve at a point gives us the exact rate of change of the function at that point. Right, everyone, what I have here is an example question that you can be asked on this kind of topic. So it says that we want to estimate the curve, the gradient of the curve at this point 2 to 8 to 8 by using these two chords. Now you don't need to draw an axis, but to visualize it better, I'm going to draw a graph. So it's going to be x, it's going to be y, and we're going to have the graph of y equals x cubed, which would be something like this. And what it wants from us is it wants we have a point 2 8, we have a point, I'm going to color this in green, we have a point 1 to 1, and we have a point 3, so the graph doesn't reach here, but 3 to 27. Now, as you can see, well, we can estimate the rate of change at this point right here. I'm gonna color that blue. At this point right here, 2 to 8, by calculating the slope of this line between 1 to 1 and 3 to 27, and this right here would be our chord. So how do we find the slope? Well, the slope is the change in y over the change in x, right? And here the change in y between these 2 points in green right here is 27 minus 1, and the change in x between these 2 points is 3 minus 1, which would be 26 divided by 2, which is 3. Part B of this question talks about how we can improve this estimate. So in the previous question we used the points 1 and 3. So now let's use points closer to 2 than 1 and 3. So let's say we use 1.5 to what would be 1.5 cubed. We can calculate that using our calculator. So 1.5 cubed is equal to 3.375. And we can also calculate, let's say, 2.5 cubed, and 2.5 cubed would be 15.625. And now, using a similar method, our change in y divided by our change in x, well, that's going to be 15.625 minus 3.375 divided by 2.5 minus 1.5. And putting this into our calculator, we get 15.625 minus 3.375 divided by 2.5 minus 1.5. We get 12.25. Now our last answer was 13. Our new answer is 12.25. And this right here, this value right here, is closer to the actual rate of change at this point. And how do we calculate the actual rate of change? Well, we're going to go on to that later on. But here, the actual rate of change would be, the real value of the rate of change would be 3 times 2 squared, which is 12. And as you can see, this approximation is a better estimate than 13. Alright everyone, so far we have talked about estimating the gradient of a function at a point, but how do we actually calculate it? Now, essentially in your exams, what you're going to be doing to do this is that you're just going to be using a set of formulas that will work all the time. But instead of blindly giving you these formulas, I'm just going to try to explain the intuitive reason behind why these formulas work. So let's just again draw a random function. I'm just going to say x and y. I'm just going to say that y equals f of x again. And it's going to be some random wild function like this. And what I want is that I want some point x, let's say. Actually, I shouldn't call it x. Let's call it like a. And yeah, I'm going to use red. So a. And the value of our function is at that point is going to be f of a. Now, again, I'm going to this time choose a point close to a. Let's say some value a plus h. And this h right here is going to be a small value, like 0.01 or something like that. And the value of our function at this point is going to be f of a plus h. Now, as h approaches 0, we have seen that the value, the slope of this curve, this line right here, the line that goes through these 2 points, is going to approach the rate of change at point A. Now, of course, in the previous examples, we did this by choosing 2 points near A, but it works just as well if you just if you pick one of these points as A and instead move one of them closer to A. So anyway, let's calculate the rate of change. So the rate of change is going to be delta y over delta x, and this is going to be equal to f of a plus h minus f of a, and the change in x right here is going to be h. So I'm just going to write divided by h. And we say that the value of our the value of the derivative of our function at a, so f prime of a, so the rate of change at a is going to be this value right here as h approaches 0. Now we know that h cannot equal 0, otherwise we would be dividing by 0, and that's the paradox of the instantaneous rate of change. But the value that this approaches as h approaches 0 is going to be our derivative. And since this works for any value of a, we can, instead of writing for some value of a, we can just replace a with x, and we can get the following formula. That's f of x, the derivative of f of x, so f prime of x is equal to the f of x plus h minus f of x divided by h, of course, as h approaches 0. Now, this is not the mathematically correct way to write this, because we usually denote this part, the as h approaches 0 part, using what's called a limit, but you're not required to know that for your GCSEs. And in fact, you're also not required to know this for your GCSEs as well. I just want to explain the following formulas intuitively. Alright everyone, now let's calculate the derivative of a function, of a concrete function. Let's say for a function f of x equals x squared. Of course, I forgot to write that. This is only correct as h approaches 0. So if our function is x squared, the derivative of f of x, now it's going to be f of x plus h, which is going to be x plus h squared, this, minus f of x, which is x squared, divided by h, of course, as h approaches 0. And what is this? I'm just going to expand this part right here. This is going to be x squared, and I'm going to write the other parts in black. 2 plus 2xh plus h squared, and then minus an x squared, and all divided by h. Now, as you can see, the x squareds cancel out, and we have an h term both in the numerator and in the numerator, a factor of h both in the numerator and the denominator. Now, we should note that we cannot divide the numerator and the denominator by h if we know that h can equal to 0, but we're saying that h approaches 0. We never say that h is equal to 0, and hence we can divide by h, and the result is 2x plus h. So for some value of h that's non-zero, the rate of change is going to be 2x plus h. The estimated rate of change is going to be 2x plus h, and as h approaches 0, this value is going to approach the correct rate of change. So, and as h approaches 0, this value is going to approach 2x. So we say that the derivative of f of x squared, f of x equals x squared, is 2x. Alright everyone, before delving deeper into the differentiation, I just want to give a quick note on the notations we use on differentiation. So we said that if we have a function y equals f of x, let's say, we denote its derivative by f prime of x. But we can also denote it using what's called a derivative operator, which is the which is called the d over dx applied to f of x. So applied to f of x like this. Now this right here is the derivative operator. It's called the d over dx. It's written as d over dx, and we apply it to a function f of x, which denotes the derivative of our function. Now, sometimes we use a shorthand to write this as df over dx, and this essentially makes the same thing. I don't think you're going to be seeing this a lot. Now, if we say that y equals f of x, we can also use a similar method, similar notation, that we can denote the derivative of f of x as y prime or as dy over dx. And these four are pretty much all that you need to know for the notation of differentiation. All of these mean the derivative of f of x. Alright everyone, now let's get on with some of the basic rules of the derivative. Now, all of these rules come from the method that we developed earlier, the approach, letting h approach 0 and calculating the estimated rate of change. All of these formulas come from that, but it's still important that you know these formulas because they are really short. Now, we say that the derivative of a constant function c is equal to 0. Now, intuitively, right, this should make sense, right? A constant function does not change, so its rate of change is equal to 0. Now, we say that the derivative of a power of x, with respect to s, of course, the power of x, let's say x to the n, is going to be equal to n times x to the n minus 1. Now, you can derive this formula using the binomial expansion, the binomial theorem, and the previous definition. But I'm not going to go over that. You should just know this, and a nice handy way to memorize this formula right here is you think as x to the n as the n going downwards and leaving one less than itself. So x squared would go downwards to be 2x to the 1. X cubed would go downwards to be 3x squared, and so on. And we call this the power rule, but I'm not sure if you're required to know that. Another basic rule that we need to know is that the sum of derivatives is equal to the derivatives of the sum. So the derivative of a sum of two functions, let's say f of x plus g of x, is equal to the derivative of f of x plus the derivative of g of x. So when you have, so let's say if you want to calculate the derivative of function x cubed, I wrote that real bad, x cubed plus x squared, well, this is going to be the derivative of x cubed, which is 3x squared, plus the derivative of x squared, which is 2x. Now, the final rule that you need to know is that the derivative of a function multiplied by a constant, let's say some constant c times f of x, this is equal to that constant times the derivative of f of x. So, for example, the derivative of 3x cubed, let's say, well, that's just going to be 3 times the derivative of x cubed, which is 3x squared. So it's going to equal 9x squared. And using these rules, you can calculate the derivative of any polynomial, which is what you're required to know for your GCSEs. Now, for example, let us calculate the derivative of, let's say, I don't know, a random function like x to the 5th minus 10x squared, let's say, plus 5. I'm just writing random numbers. Now, using this sum rule right here, we can say that this is the derivative of x to the 5th, which is 5x to the 4th. And then minus 10 times the derivative of x squared, which is 2x, plus the derivative of 5, which we know is 0. So this is going to be equal to 5x to the 4th minus 20x. And this right here is our derivative function. So if you're asked to calculate, let's say, the gradient of this function right here at, I don't know, x equals 5, for example, that would be the same as plugging x equals 1 into this result here. So what you get is 5 minus 20, or negative 15. What this means is that at x equals 1, the slope of the tangent line to the curve, to this curve right here, is going to be negative 15. And using this, you can pretty much calculate any derivative you want for polynomials only. Alright everyone, now sometimes in questions you may be asked to find the equation of a tangent line or a normal line of a curve at a point. Now for these you should know the formula y equals mx plus n, and that the value m indicates the slope of a line, and the value n indicates the y-intercept of that line. Now, we know the slope of a, let's say, for a function y equals f of x. If you want the equation for the line that's going to be tangent at point at say some point A, the tangent to that function at point A, or A of f of A would be more correct, I guess. Now we know that the slope of the tangent line at that point is f prime of A. So we can find the value, the value of m is simply going to be f prime of A. And to find the value of n, you must remember that the line of tangency for a curve, let's say like this, has to go through the point of tangency in that curve. So we know that this line that we're trying to find has to go through the point A of A f of A, meaning that this equation right here must satisfy this point. So f of A must equal f prime of A multiplied by x, which is A, plus n, and using that you can figure out the value of n. Now you can do a similar method to find the equation of the normal line at a point. And to know this, the normal line is pretty much the line perpendicular to the tangent line at that point. And to know this, you have to know that if m is the slope of a line, then the slope of a line perpendicular to that line would be -1 over m. And you have to know this, it's not too difficult to memorize. So again, you have to use a similar method, but instead of this time using the slope as f prime of A, you have to use -1 over f prime of A. And this would be the slope of your normal line, which again, you can find the value of n right here by considering the fact that the normal line has to go through our point of tangency, which is A of f of A. Alright everyone, now let us consider the topic of stationary points, turning points, maximum values and minimum values, which are pretty much like applications of the derivative that you are required to know. Now, a stationary point it's just a simple definition. And a stationary point is simply a point where the gradient of the slope of tangency is 0. So pretty much it's a point x. It's a point on a curve, so x f of x, such that f prime of x is equal to 0. Now this could be in many forms and shapes. For example, let me draw two graphs here. Here I'm going to draw the graph of y equals x squared, which is going to be something like this, if I can draw. And here I'm going to draw the graph of y equals x cubed, which is going to be something like this. Now in both of these cases, we can see that the derivative at point 0 is 0. So we would denote the stationary point of this function as 0, 0, and this as 0, 0 as well. Now if it was, say, a different function, for example x squared plus 5x minus 2, let's say, the stationary point, to calculate the stationary point, we need to get the derivative, which would be 2x plus 5, and the derivative, and we need to set this equal to 0, which gets us the x value of -5 halves. And we need to put this x value into our function, and that will give us our stationary point. Now, let's consider the concept of a turning point. A turning point is pretty similar to a stationary point, but it has one mild difference. A turning point is pretty much a point where the derivative, the slope, switches signs. So the derivative, it's the point where the derivative goes from negative to positive or positive to negative. So again, consider the function, for example, y equals x squared minus 2x plus 2, let's say. And if we draw the graph of this function, it would be what would this be? This is x minus 1 squared plus 1. So it would be something like this. It intersects the y-axis at 2. So it would be something like this, if I can draw correctly. Okay, whatever, you get it. So at point 1, the value of 1. Okay, no, I must have still not satisfied. There we go, that's pretty good. Okay, this value is 2, and this value is 1, and this is 1 as well. So as you can see, if you calculate the derivative of our function, or I mean, we don't need to, like, you can see that the derivative here is negative because the slope of tangent lines is negative. And you can also say that the function is decreasing at this region. So at this region, below 1, before 1, the function is decreasing. And for a similar reason, after 1, function is increasing, so the derivative is positive. At the point 1, at the point 1, 1, derivative is 0. So we could say the point 1, 1 here is a stationary point of the function. But we could also say that it is a turning point of this function, simply because the derivative goes from negative to positive at this point. Alright everyone, now let's talk about the maximum and the minimum values of a function. And this is simply, basically, once you find the turning, if the function has a turning point, the value of turning point, the y value of that turning point will either be the maximum or the minimum value of that function. Now, we can't say maximum or minimum. The more precise term is local maxima or minima, and I'm going to explain that in a minute. But for example, if we have a parabola like this, again, this right here, this point right here, would be a turning point because it's decreasing, it's 0, and it's increasing. So this right here is a turning point, and which shows us that the y value of this function, so this length right here, is the minimum value of our function in this case. Now let's draw a more complicated function as an example. So something like, let's say, something like this. Now, if you try to find the turning points of this function, what you'll get is that you will first have to set the derivative equal to 0, which would give you these 2 points, and these are in fact turning points because, as you can see, it's increasing, it's 0, and then it's decreasing, and then it's decreasing, it's 0, and then it's increasing. So at these points, these are the turning points, and hence the tangent slopes are equal to 0. And as you can see, as you find the coordinates of these 2 points, the y value of this will be the local maximum of our function in this given region, right? And the y value of this point right here will be the local minimum of this region. And the reason it's the local maximum minimum and minimum is that this function's maximum and minimum values are, well, infinity and negative infinity, right? This function goes down as much as it can. This function goes down as much as it can, and as much as it can go up to, meaning that the minimum value of this function is negative infinity, and the maximum value of the function is positive infinity. But the function's turning points are still these values, and we call these values a local minimum or a local maximum. Now let us talk about the concept of the second derivative of a function. So if we have a function f of x, as we know, we denote its derivative, so its rate of change, as f prime of x, or by dx of f of x. Now, the second derivative, or the second order derivative, is simply the derivative of the derivative, so the rate of change of the rate of change of a function. And we denote this by f double prime x, or the second derivative operator, d squared over dx squared of f of x. And defining the second derivative of a polynomial is not difficult. So for example, for say a random function x cubed minus 5x squared plus 3x minus 2, let's say f of x is equal to this. So we know that the first derivative is going to be equal to 3x squared minus 5 times 2x, so minus 10x, plus 3 and plus 0 from this. So the second derivative of x, or f of x, is going to be equal to 3 times 2x, so 6x, minus 10. And that's how we find the second derivative. Now, the second derivative actually has some meaning on a graph of a function. So let's say we have a random graph like this. Say, now we know that the derivative of a function shows us if the function is increasing or decreasing. So if it's increasing, the derivative is positive. If it's decreasing, the derivative is negative. Now, for the second derivative, tells us about the concavity of the function. Now, if we say that, for example, if you look at this curve right here, if I draw it in red, we see that the slopes of the tangent lines here in this region right here are decreasing, meaning that in this region right here, the second derivative is negative because the slopes of the tangent lines are decreasing. But if you look at this region, for example, we see that the slopes of the tangent lines are increasing. So in this region right here, we can see that the second derivative of our function is positive. Now, if the second derivative of our function is positive, we say that function, the region, in that region, our function is concave up. So let me draw that in another color, or say like this, concave up. And a concave up function pretty much looks something like this, or it can be this too. So if it looks like this, as you can see, it does look like this here, it's concave up. And if it's negative, we call it concave down. And a concave down function is something like this, or something like this. And as you can see, in this region it is concave down, like this. And just like for the derivative, if we said that the point where the sign of the derivative changes is the turning point, we call the point at which the sign of the second derivative changes, so where the function goes from a concave up to a concave down point. So for example, it would be around like this point right here. We call this point right here the inflection point, or the point of inflection. And the inflection point is a point where the second derivative of our function is equal to 0, and the second derivative of our function changes sign going through that region. So here it's the second derivative is positive, and here it's negative. So we say that this point is an inflection point. Alright, that's pretty much it for everything. Thank you guys for listening to our class, to our lesson. And we'll see you in the next lesson, I guess. And also, don't forget to like and subscribe to the channel. It really does help.